Hello, my name is Chae Yunbyung. Let's begin my presentation. My presentation today will cover the following contents. Given a motor input, it is necessary to analyze what state the robot will be in. This process is called state estimation. The rigid body robot can quickly estimate state through forward kinematics using the angle of the joint and the length of the ring. However, it is difficult for soft robots to estimate states on given motor input. Since soft robot control is a complex movement that is hard to analyze, it is useful to train neural network that performs state estimation from motor inputs. In order to learn efficiently with little noise, I utilize active learning method. Hence, I experimentally validate the proposed methods to train multilayer perceptron (MLP) for state estimation. And it is experimented with an active learning methodology using model uncertainty. Soft body robot is difficult to control like a kinematically redundant robot. So it is more difficult to apply them in real life than rigid body robot. However, a recent study aims to analyze and accurately control the soft robotic system. Because soft robots take great advantage of their safe interaction with the environment, it can be applied to more fields than rigid body robot. It is challenging to analyze soft robotic systems using conventional methods since they have additional properties such as continuity. For reducing continuity, I leverage a kinematics tree model which has prismatic and revolute joints alternatively. In short, we analyze soft body robot with rigid body model. We utilize neural network which optimizes motion of soft robot, so we mine data trajectories with curve. We assume that collecting real-world data is difficult because human operator should label every trajectory. I present the active learning method which query informative trajectory data for training neural networks. I referred to this paper to explain the relation motor input and trajectory output. We proposed a new approach that directly represents both time-varying commands and the resulting state trajectories with a function. It is a representation across space and time with initial and target states as inputs. This deep network can be trained to output an accurate temporal profile of the optimal command and state trajectory for a point-to-point reach of a nonlinear limb model. I refer to this paper to implement active learning method for regression. It proposed a new theoretical framework casting dropout training in deep neural networks as approximate Bayesian inference in deep Gaussian processes. This mitigates the problem of representing uncertainty in deep learning without sacrificing either computational complexity or test accuracy. I referred to this paper to implement active learning method for regression too. It proposed a fast active learning algorithm for regression tailored for neural network model. Active learning is a framework in which a machine learning algorithm may choose the most informative, unlabeled data samples and ask an external worker to annotate them. More precisely, we are given another set of points called the pool, which represents unlabeled data. We need to choose as few additional points from the set as possible to achieve the desired quality of the model. To achieve this goal, we use acquisition function which ranks the points from the pool. The proposed method is a model that outputs time-varying trajectory when the motor input is given. MLPQ outputs a joint angle sequence over the time step given a motor input. MLP-R outputs a link extension sequence over the time step given a motor input. The link extension scales local position. After initialized joint local coordinate, further kinematics algorithm maps three of them to the output trajectory. I applied dropout layers to each MLP. It probabilistically ignores some weights when approximating the trajectory, so it can avoid overfitting to train dataset. Furthermore, we can get the stochastic trajectory and we can get the stochastic error. If we give the same model input to model repeatedly, and we can derive the error distribution. If we get the high variance distribution, we can say that the model has high uncertainty about this input, and vice versa. Let's see model output animation. Left side is output with dropout layer, and right side is output without dropout layer. As you can see, without dropout layer, model overfit trained dataset, so output trajectory is smooth. But with the dropout layer, because the model ignores some weights, the output is not smooth. Now we can categorize the motor inputs with the high uncertainty input and the low uncertainty input. To estimate soft robot state with sample efficiency and less noise, I collect the high uncertainty inputs and query a pair of motor input and output trajectory. Through this process, model can be actively learned. We train the model with dataset which is composed of log spirals. It contains many linear trajectories and a few non-linear trajectories. So the model has a problem with training non-linear trajectories, while linear trajectories can be easily trained. I found out that the model has a higher uncertainty and higher error about non-linear trajectories input than linear trajectories. So, to actively learning, my model frequently queries about the non-linear trajectories. In conclusion, after the model querying informative trajectories, the test error decreases. With fewer data, the model can approximate the target trajectory. My presentation is over, and thank you for listening.